Video solution to bonus problem 1 for kinematics. We're going to begin by finding this equation or deriving this equation or formula, which simply combines both the x and y components. So we're going to start off by with our kinematics equation, where x is equal to vt plus half at squared. We can simplify that by introducing what we know to be the velocity in the x component, and we also know that the acceleration is equal to 0, so half at squared is simply eliminated. So we're left with x is equal to our initial velocity times cos theta times time. If we rearrange that for t, we are left with x over initial velocity times cos theta. If we sub that into the equation that we had up here, except for the y, the distance in the y direction, we can sub in this component into t, and what we know to be the velocity in the y direction, which is simply initial velocity times sine theta. So once we do that and simplify that, we are left with y is equal to x tan theta minus gx squared all over 2 the initial velocity squared times cos squared theta. From there, we then sub in what we know to be the y component, the x component, and the initial velocity at the point just over the mountain, right? Because we know that for both projectiles, when fired from those two angles, will pass through that point. It'll have to pass through that point, and that is how we find the angle. So, as you can see, we simply plug those values into this formula, simplify that down until we get what looks to be a quadratic formula. We can then let x equal tan theta, and that simplifies it even further and puts it into something that we're more familiar with, that we can work with. And you can see that we've made sure that we've isolated the x squared term, which makes our life much easier. We can then plug it into the quadratic formula. From there, we get these two positive x values, right? And we know that because it's a range between those angles, they will both be two positive values. There won't be one negative, one positive, and there won't be two negative values, because we know it exists. Then if we let x equal tan theta again, we can make theta equal arc tan of both of these x values here, and then we're left with these two angles, and that'll be our minimum value and minimum angle, and our maximum angle, which is we can then derive the range from. So we're left with 75 degrees and 50 degrees. From there, we can then use the formula or our identity, which gives us the maximum range for a projectile, and that is simply 2v squared times sine theta times cos theta, all on g. If we then sub in the two angles that we have, we receive these, or we get these two lengths, right? 3,065 meters and 6,276 meters, right? But we know from our diagram here that that is the distance. These are the distance from our initial and starting point here. So what we need to do is we need to minus the distance from our mountain or our cliff here, and plus that 300 meters, which from this whole cliff here, right? So as you can see, the distance to the side of the mountain, so this far side of the mountain, is equal to 2,800 meters, right? 2,500 plus 300 meters. Then what we can do is, with these two values here, we simply minus that value, and we have these two distances, right? And these are the distances, right, which will give us the range at which the ship is safe from being hit by a projectile from the shore of this island here. So we get 3,476 meters and 265 meters as well, right? So therefore, the ship will be protected when it is in a position less than 265.1 meters from the shore here to the isle of the island, and further than 3,476 meters from the shore. So this distance here, from this distance here, if the ship is anywhere between there, it'll be safe. And again, if the ship is anywhere between the edge of the shore of the island and 265.1 meters from there, it'll be safe again.